Here's my next problem.
So
It's
if they
gonna
were,
change a tad. Oh, go ahead.
if they were equal real quick, so if it was 1 and 1, then the limit.
Limit would be 1.
Okay.
Isn't that cool? It's actually a theorem if you want to make a theorem out of that. You're like, if this limit right here is equivalent to that limit right there, then limit as x approaches 2 would equal that number. You can call this like C. If that's C and that's C, then limit as x approaches A is also C. And you can make a theorem out of that. Isn't that cool? Awesome. Now watch this. I'm going to change one thing. You can tell me what happens with all these answers. This one, and your cool question. I'm going to include it. So I'm going to include his. Here. A, B, C, and that's D over there, right? Here's my change. So let's erase all the answers. And here's my change. Are you ready? That's my change. So to get this whole section now, we just got to change little pieces. So that's not filled in. I don't know if that looks like there's a hole in there. There's a hole in there. Take that chalk off there. I'll use this thing. It can't go away. There we go. That's better. So I got 2 opens there. Hey, it still passes the function test, though, right? All right. What's the answer? Write it in. Limit as x approaches 2 from the left side. All right. There's x equal to 2. I jump on the graph, close. I approach in. What's it? Remember, it's all about limits. It's not who cares what's going on at exactly 2. It's about as I'm getting closer and closer, as close as possible. What's it keep getting closer and closer to?
1.
That's it. Same answer as before. What's this answer right here? Right? -1. These don't equal. What do y'all think? They're not equal.
Still doesn't exist.
Does not exist. I guess we're getting all the same answers. Well, except for his question. Come on over here. What's f of 2? Now that means what's going on at exactly x equal to 2. What's the function value? I see 2 holes. So what do I put here? There you go. Undefined, does not exist. Right? Is that cool? Awesome.
And if they're both equal from the left and to the right, what's the limits of the third option?
Oh, this guy right here? So if that was, let's say it was 5.
And the second one.
And this one was 5. And boom, 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 that's a 5. Isn't that cool? We'll do one of those too. I love your curiosity. We'll do one of those. We'll make a picture of that. We'll see what it looks like. Awesome. Hey, I have to do one more of these. Ready? Ready? This is 4. There's my dot. Okay, what goes on with this problem? Does it pass the function test? Yeah, it's a function. It's a function, right? Draw vertical lines, or you hit it once. Well, aren't these 3 answers the same again? What's that though now? See, the pre-calculus is whatever sometimes get everyone. You get all 3 answers the same about the approach, the approach. But what's this now? It's way up, it's a 4 now. It's up there. And it's funny, this had nothing to do with these. Welcome to calculus. This had none, that 4, you know? That was going exactly at that.
It's just a dot, which just picture as a straight line, I guess.
That's right. That's a good way to look at it. That was good. All right, I got to do your scenario. Are you ready? So this was yours, and it was a good idea. Oh, what's the name again? Arnold. I'm doing yours. Here it is. You ready? I'm keeping that there. I'm just going to go like that. All right, I'm going to wipe out all the answers. You ready to do this? Get your eyes on that curve. Jump on the roller coaster. Approach 2 from the left side. What are you getting closer to? From the left, what are you getting closer to? 1. How about from the right? 1. These are the same. See, people get worried about this. They think, oh, I should put DNE here, because they see a hole here. But no, 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 no. What's this answer? By this theorem. If that's a 1, that's a 1. What does this have to be? And we can see it actually. Can you all see this? As you approach 2 from both sides, the function kept getting closer and closer to a what? To y value 1. But there's a hole there. It's all in the approach, as infinitely close as possible. Right? This is still a what though? It's still a 4. Isn't that cool? So that interesting one? Don't think like here, oh, it's got the open, I have to put D and E. Absolutely not. If these are matching. It could be a nice hole there. That limit exists. The limit exists, doesn't it? Cool? But what was f at 2? 4. Alright. Now watch this. truly means that when I just did that, then basically this is nice and what? Smooth through there, okay. So they did it right through there, went right through that for him. So do these stay the same? I don't see nothing start. Well, let's still do it. As you approach 2 from the left side, what are you getting closer and closer to? 1. As you approach 2 from the right side, what are you getting closer and closer to? 1. Those are the same, so the limit from both sides has to be a what? 1. Now what's this though? 1. Don't agree? 1, 1, 1, 1, 1. So this must be building into something else in calculus at school. It is. Unfortunately, when we're in section 2.2, that's in section 2.5. Maybe they wait too long for that. You know what that's building on? Do you notice that the curve's like connected? They call that continuity. So when something's going, what we just saw, if you have to define, like in calculus, how do you define continuity? How do you define that a function has to be continuous? We got to explain this in theory. The idea that what? This limit right here, it's the same from both sides, this number, and it has to equal to what? The same value there. And that makes it all what? Nice and connected. Isn't that cool? That's how you actually, in mathematics, in calculus, you define continuity by that concept. We just got to write it with goofy notation, right? We just got to, you know, the idea that these limits have to match the what? These numbers right here have to match for this to work. What did I have before? A 4. You go, is that connected? No, it's not connected, right? Think of this as a roller coaster. It's not connected. It's not continuous. You'll fall in the hole and you'll die, right? But to make this thing connected, that value there has to match what? This guy. Isn't that cool? And if you get that right there, that, you got it. Now don't worry, that's coming up, not today. That's section 2.5, right? You're saying, oh, you got the function being continuous. Isn't that cool? So that's how you define this word continuity in continuous functions. Evan, I think we've hit every scenario, but I'm still going to put some other graphs up here, okay? I think we hit all the scenarios, right? It's like nothing should be able to stump us. Well, what about like asymptotes? Have you ever seen asymptotes before? I mean, the book's going to get into that. I think he waits too long, but that's okay. He waits till this section to get here. I don't think it hurts us if we just look at some pictures of graphs of asymptotes. Do you? I don't think so either. So let's just draw a graph, and you know, I'm going to make one up. Ready? Well, in fact, I'm going to erase this. Find a limit as x approaches 3 of the function. Let me look for a good one. How about 2 over x minus 3? Now, if you want to make this graph with your calculator, you can, but now notice I put the function in here. I want us to find this. I'm going to do one more thing though, okay? I'm going to do a little minus there. So you and I are trying to find the limit of this function equal to 2 over x minus 3 as we approach to the x value 3 from which side? From the left. And you're allowed any way you want to do this. You can use any technique on your test to do this problem. But I encourage you, you all are so good at graphs. Why don't we just make the graph and look? Right? You go, I don't know how to graph that. I wouldn't graph this. This is called a rational function. Remember, they got asymptotes. And it's got vertical and horizontal asymptotes. So we got to talk about, in this rational function, let's just go over here, a little pre-calc review. You know, a little review of pre-calc. How do you graph the function f of x equal to 2 over x minus 3? So you and I can look at this graph so we can answer this question. Because I want to answer this question graphically. You might have other ideas, and I think that's good, actually. You might go, I got another way to answer this question. But we're going to answer this question graphically. Well, I just need to know how to graph this. Well, that's called a rational function. And it's got, first of all, a vertical asymptote. Find a vertical asymptote, but we got to set the denominator equal to 0 and solve for x. So what makes x minus 3 equal to 0? Alright, so when there's a vertical asymptote at x equal to 3, let me just draw that then. Alright, so this graph. Aha, now you know why I asked you what's going on at 3. Here you go. That's a little vertical asymptote. That just means the graph's going to curve and bend into this thing like that. Now, does it have a horizontal asymptote? Yep.
Yes.
know that? She just knows it, right? That's good, she knows her pre-calc. Oh, and if you wanna know with these rational functions, if the higher exponent's on the bottom, it's always y equal to 0. So the horizontal asymptote is the x-axis. But if you wanna know something, if you're like, oh, I forgot that pre-calc, or, you know, it's just been a while since I had pre-calc, like a year. Like Jordan is like, oh, it's been a year. If the higher power of this exponent, see that little power right there? If the higher power is in the denominator, then you always got it at y equal to 0. Cool. That's what the horizontal asymptote is. Now, if you're curious, like, well, what if the powers are the same? We'll get into that later this week. We'll get into that later this week. We don't have to harp on that now unless you really were curious and like, no, tell me about it now.
You said it equals.
Yeah, you do stuff like that, yeah. And it's, see, they really get into this in 2.6, I just thought it'd be neat to talk about it right now, since we're doing limits graphically, right? So, where's the horizontal asymptote? Right here. And it's always gonna be here in a rational expression if the higher power of the exponent is on the bottom. Alright, so there it is, but how do I get the graph going? I wanna make this graph. And some of you are like, well, I use my graphing tool. Okay, that works. But let's say I have this calculator, and I can't make the graph. Can I hold it up?
Yeah, hold my joke.
Oh, yeah, but so I don't have the graph, so I don't have that thing, I gotta make this graph on my own. So I got the hardest part done, I just gotta plot some points. I think I can do it with 2 points. Let's make a little table. Just pick an x value on this side, and this value is 3. Like, what's going on at x equal to 2? And what's going on at x equal to 4? I'm just trying to make the graph, right? Well, I think with 2 points I can make this graph. What's going on at x equal to 2? I get -2? Did I do it right? What's going on at x equal to 4? 2. Alright, so let me plot these. At 2 it got to a, I got the -2. And at 4 it got over to a 2. Now you know what happens with these graphs? They bend towards the asymptotes. So take your pencil or your pen, and just swoon. This graph's just doing this. Woo! Woo! But now I can answer this question. In fact, did I have to make this whole graph to answer this? I only needed which side? I only needed the left side. I actually graphed too much, didn't I? That's okay. Wait a minute, plot 1 extra point. Y'all agree? But now we can answer this question. So even though this is going to be asked in section not 2.2 but 2.6, we all can do this now. As you approach x equal to 3, from which side? So go jump on the function. Where? Way over here. You can if you want, but I say get really, really close to the what? To this tree. Jump on it and ride it, ride it, ride it, ride it, ride it. What's going on with that y value? Where's that y value going? It keeps going down and down and down and down and down. So what is that? Negative what?
Infinity.
Negative infinity. That's the answer. I'll put it right here. I just thought you'd be curious about that. I thought I'd show it to you now. That's in section 2.6. You're like, oh, I can do that now. Man, look at any graph, you'll find the answer. You can find a limit to it. Isn't that neat? I just need the graph. Cool?
So I guess you only have to understand the pattern, whether it goes up or down.
You got it. Now watch how good you are. What's this answer? Just look at the graph, right? What's the limit as x approaches 3? I put a plus there of 2 over x minus 3. Right it, where you going? Positive. Now, are these the same? No. So what has to be this answer? And I think you can see it in the graph. What's the limit as x approaches 3 of 2 over x minus 3? I heard it, the answer is 1. See, that's a powerful statement. As we indicated, these two would have to be the same. Now yes, this is true everyone. What if that was infinity and that was infinity? Then you could put what? That happens sometimes. That'd be one of these, or both of the two sides of the rational function went up like this. You go, oh, that's going towards infinity and that's going towards infinity, so the limit is infinity. Cool. Everyone, man, you were good with this. Everyone okay with that? Even though, when does this really get covered? Yeah, but why would we do it now, right? Isn't that cool? Hey, I got another cool one. Thought we'd hit it now. Here you go. Again, this is really in 2.6. I just thought it'd be fun to do it now. Get this out of the way. And when you see the picture of the graph, right? I'm telling you, if you know the graph, you can get answers. If you know the graph, you can get answers. What's the limit as x approaches? Let's have fun with that. The author thought you should wait till section 2.6 to do this. I'm like, nonsense. They can do this now. Let's write it. There's our picture. We see the graph, everyone. I think this has something to do with it. I think you all see it. Write it, but what x value are you approaching? Where is x equal to infinity? Way down there. So I wouldn't jump on the roller coaster. Get on there and ride it. Just ride it. Where are you going? I mean, this thing's not going down here, is it? What y values they keep getting closer and closer and closer and closer to? You got it. So isn't this neat? With rational functions, it's just the Horace. Isn't that cool? When you're dealing with a rational function like this, and it's got a horizontal asymptote, well then your limit as x approaches infinity is the Horace. I'm abbreviating Horace as the horizontal what? Asymptote. Whatever that is, that's where it's going. That's what I mean. That's why I thought, you might as well see that. You go, if you're going to head towards the x equals infinity, you're heading towards the horizontal asymptote. That should be your answer. You bet it is. You bet it is. But not all rational functions have Horaces. Some have slant acids. Do you remember that? Like a slant asymptote. So we'll wait till 2.6 to do the slant asymptote thing. Yeah. So I went super job at that. There's another graph I got to do. That's kind of weird. This is 2.2. We really hit everything in 2.2. One of my favorites is, I should show you this one graph. I don't put this on the test because if I use software to build this, I don't think it would look good. Do you have your textbook? You got it there?
Yeah.
Would you look at everyone, number 6? And there's something funny looking in the graph. Oh, this is page 96. Check it out. Just look at number 6, and you see something funny.